that's the part that's a little more challenging when you've got function pointers. For that part, I had 2 screens of code and we dealt with it. It was just marvelous and done. So it doesn't have to be too much.
I don't know, that doesn't make it feel comfortable.
Yeah.
2 whole screens? Good.
I don't expect that all of you necessarily went as exhaustively as I did.
Okay.
I had some nice data structures that I made that allow you to be conservative about these varargs things in a reasonable way.
Is it open source?
Is what open source?
Is your code open source?
After the 7.
That would defeat some of the purpose. We can take a look at it. Essentially, for the next project, you're going to be using call graphs again, right? But I'm not going to have you necessarily do anything with function pointers or anything like that. So I don't expect that to be a problem at all. We might take a look at it on Tuesday to see how I went through things.
So the project won't be up today?
I'll probably put project 2 up like late this evening / early tomorrow morning or something like that.
Because weekend and
Yeah.
instead of partying, we will be responsible students,
Yeah. And if anybody hasn't submitted a critique for this week yet, get that to me sometime. The next, let's say maybe after the project is due and the panic has subsided.
I assume you want to submit it on courses or
Email, courses,
doesn't matter to you?
whatever.
Yeah.
That's that doesn't make too much of a difference. I'm not going to present anything today,
Okay.
so it's just going to be you. Let me download your slides. Well, hopefully we actually get time to discuss, right? One of the things that I've been disappointed about is that we haven't had real discussion time, and usually it takes 40, 50 minutes to have people know what a paper is doing, and then you can only after that actually tear apart. Oh, I can't connect to the server. I'm not going to be able to. Give me a moment. I can't access your slides yet.
So it's completely okay to make presentation like say 10 minutes and then leave the rest for discussion.
No, follow the guidelines on the website. Follow the guidelines. The guidelines are there to help you, not to mislead you or serve as a counterexample. Do you have transitions? Do you want the PowerPoint version, or is it just PDF?
Okay, PowerPoint is fine.
PDF, okay. I will give you grand access to LibreOffice. Which may or may not display things exactly. LibreOffice is actually some of the
I tried
highest
making
quality software
presentations
that
with that,
exists.
and it's a pain.
So LibreOffice managed to, with the help of some other companies, get their bug rate down to 1 bug per 1,000 lines of code, and industrial code is 1 bug per 10 to 100 lines of code. So LibreOffice is actually better.
They don't have many features.
That's fair.
But yeah, it's not the amount of bugs, it's the amount of features.
It's really difficult to make presentations
Oh,
with
no.
open source software unless you do Java.
Well,
I don't have many problems. Most of my presentations aren't great,
Right,
but they're okay.
right.
They're focused
Serves
things.
the purpose.
Yeah. You don't want things to be too flashy anyway, in my opinion.
Yeah.
1 bug for 100 lines of code.
And industrial code tends to be 1 bug per 10 to 100 lines of code.
That's ridiculous.
Yeah.
And that's why this course is so important.
Yeah.
I'm actually really surprised by that.
Yeah, no, welcome to the fallibility of people,
Yeah, really.
right? We suck. That's the lesson. That's why the teaser in the blurb for this course was, people are bad at this. Let's try and get computers to do it.
Yeah.
That's still tough, but at least it's something where it's consistent.
Yeah. People are also lazy. Big computers do.
I like that too. Not gonna go for it. There we go.
Okay.
Whatever. Okay. Enjoy.
Really? That's quick.
Yeah. Is it not?
It's not moving.
Okay, so just press left and right to get it. Okay, you got it.
Okay, so presenting Eraser, which is a dynamic tool to detect data races in multi-threaded programs. Introduction, basically multi-threaded programming is really difficult and error-prone because there are a lot of threads which go and try to synchronize and read and write data from. So especially for shared data, it's a big problem. Whenever different threads try to read and access the same area of the memory. Mistakes in synchronization can produce data races and they're extremely hard to debug. Eraser is a Eraser dynamically detects data races in log-based multi-threaded programs using algorithm, which they called it as log-set algorithm. So, how data races occur? Well, as I said, data races occur when there are a lot of threads which are trying to read a certain part of the memory, and there is someone else who is trying to write at the same time. So that's one case when data races can occur, and also there should be some mechanism to prevent these data races, right? So if there is no explicit mechanism provided by the code to take care of these things, then data races can occur.
So what do you mean by simultaneously?
So basically, say if there is say at the same time, right?
Oh, can I have a data race then on a single core machine?
Single core machine, yes. If you have different threads on a single core machine, yes. So software threads are something like where so what modern operating systems do is they create software threads, right?
Mm-hmm.
So there are a lot of threads running on the same core, which is basically focused on using more resources.
Okay, but even with a single core machine then, you can have multiple
Data races.
accesses at the same time.
Yes.
So the notion of time there is a little fuzzy, right?
Right.
Because it can't actually happen at the same time. There's a logical time.
Right. Okay. So previous work, when the paper was presented, from that time the previous work was monitor concept by Hoare and happens before relation by Lamport. So before this happens, before relation came, there was this monitor code which was pretty famous at that time, and all it did was basically it will have one protected zone where it will monitor all the shared data accesses. And shared data, the notion of shared variables does not exist out of that scope. And since modern programs have like huge amount of data sharing, especially if you go at server levels where there are a lot of servers trying to access and modify the data at the same time, this concept is not really helpful. So then came happens before relation. By the way, they are all static analyses, and this was the first paper which attempted at looking it at through a dynamic approach. So basically, it used to check at compile time.
This is true for the monitor concept. That's not necessarily true for happens before.
Right.
Yeah.
So there are like after this paper came, there were a few papers which tried to look at that and
Happens before is also a dynamic technique.
right.
Before it's paper.
But it's not really helpful. We'll come to that. So happens before technique. Basically, all this technique does is try to follow a partial order of threads trying to access a shared variable. So basically, all it says is within a thread, a program follows sequential order. And across threads, if one thread accesses a synchronization object, so by synchronization object, it means the objects which have been provided by the programmer with locks. And so if one is trying to So if one thread is accessing a synchronization object and another accesses the object by a different thread, then the first access happens before the second object. And that's the notion of this whole concept. Okay, so yeah, this says the same thing about it, saying that the lock should be explicit. So can anyone think of a place where this can be a problem? So basically all it says is there are two threads and one thread, if two threads are trying to access one object, one thread tried to access one object, and when another thread is trying to access that, it should happen before the second thread.
So
But the notion of time, as he said a few minutes back, is a little fuzzy here. So
when you start to move into the example, I think it'll be clearer
Right.
how the problem can arise.
So basically, you have thread 1 and thread 2, and there is a variable y which is not being protected by a lock, and there is this variable v which is protected by the lock, right? So as per the concept, this should happen before thread 2, right? So now you have a lock and v equal to v plus 1, and then you unlock. Again, you have a lock, v plus v plus unlock, and this is happening before this. Everything seems perfectly fine, but there is a problem.
Thread 1 could execute earlier than thread 1?
No,
Thread
so
2
how?
how?
Yeah, because
No.
the algorithm is trying to schedule it
Schedule.
in this way, right?
Thread should may be executed before thread one.
Hmm?
Thread should may be executed before thread one.
So in that case, the arrow will go down towards thread 1, right? So this will happen before that.
Yes.
So it was
And
fine. Then.
No, and then y would be unprotected in any way, right?
Yes, that's one case. That can happen. But so basically, it is highly dependent on scheduling of algorithm,
Okay.
scheduling by operating systems, right? So say in one case this happened, but again now there was some problem over there, and that thread was slower, and this thread executed faster. In that case, then they will try to access it at the same time, and that can be a problem. So there is a data race on Y, as he said, and yeah, we discussed that, right? So yeah, when both threads access a shared variable and accesses are not ordered, then it can be a problem. And one thread ran faster or slower than the other thread,
Excuse me.
then it can be a problem.
We can put the lock on the etc.
On Y itself.
On Y.
So what he's trying to say is that, so this is highly dependent on scheduling, right? So suppose this was scheduled before this, but again, this thread ran much faster than that, and this came before that.
So
To the lock.
the underlying problem here is that you've got this happens before relationship that's created by the synchronization mechanism, right? And so it looks like there's an ordering between these things. And because every event within a single thread is also totally ordered, it looks like the access of Y over here happens before the access of Y over there because of the partial order. But that partial order is very scheduling dependent. So it's hiding a potential data race that could occur in a different scheduling. And I think your suggestion is that couldn't we just change how the lock is set up? And the answer is yes. But very commonly people get their locking mechanisms wrong. And so the whole point is we want to be able to detect when they've gotten that wrong.
So what are the issues with this algorithm? First thing, it is very difficult to implement efficiently. Why? Because it requires per thread information about concurrent accesses, which is a huge amount of information. And then it is highly dependent on interleaving produced by the scheduler. So then so this is a lock set algorithm implemented by Eraser, which is pretty straightforward. So all it does is there is a notion of locks underscore held T, which is a set of locks held by thread T. So basically it contains a set of all the locks which are contained by thread T, a particular thread. Okay? And then for each variable V, you initialize CV to the set of all locks when the program starts. And then on each axis of V by thread T, you take an intersection of all the locks held and the locks held by that particular thread at that point of time. And that you update with CV. Now, if at any point of time, if the set of CV is null, then it issues a warning saying that you could have a potential database. So yeah, by example, if you look at this, say initially the logs head was empty, and the CV was mu1, mu2. So basically, the whole program has only 2 logs throughout the execution of the program. Okay, one more thing. The CV, the set of CV, the total set of logs. Yeah, so before starting, it contains all the logs that can possibly be taken by thread T. And then you take a log mu1. So since you have taken a log mu1, logs held becomes mu1. And then, as the algorithm said, you take an intersection of CV and the logs held, and it becomes mu1. Yes.
I have a question. So this misalignment between statements, is it on purpose?
So this is
or
telling,
not?
yeah. So that is before this log happened, right? So
Okay.
before this log was taken, at that point when the program started, this had null and that had mu1, mu2, right? And when the program executes, you have a first log taken by the program mu1, then logs held is mu1, and CV is intersection of mu1 and mu1 comma mu2, which is again mu1, right? So now at this point when the v equal to v1 update is happening, at that point it is fine because CV is not null, right? But when you unlock it, again CV is not null, logs held is 0, and when you come to log mu2, at that point this logs held is mu2, but then the intersection of mu1 and mu2 is null. So you could have a potential database over here. So all it is trying to say is whenever throughout the program execution, if a thread is updating something, it should have all the logs.
And another thing, so idea that this program's column could be executed by multiple threads.
Yes. But each thread will have its own set of CD.
So you said you should have all of the logs.
Yeah. So they will modify it.
Okay,
Because this is
I
the
think
basic
that
version.
still doesn't quite reflect this version though. It's not that you want to have all of the logs.
When you are updating a variable v, at that point, you should have these logs.
You should have a consistent log.
Yes.
So
All
it
the
just,
time.
it just tries to
Right.
make sure there's one consistent log.
Right.
That's not a requirement for it to be true, like, for proper execution, is it?
Right, that's the point. So this is too strict, right? As you pointed out. So this is too strict. So what are the common cases which generally happen in programming, which we are aware of, which will never cause this, which does not cause a database?
One writer, multiple readers.
One writer, multiple readers, right? That's a common problem. What else?
So we go. What I recall from the paper where you only during initialization you access
Right.
variables, and then afterwards during the execution they only give the out.
Right. So if all the thread is trying to read a data, there will never be a data race. It's not a problem at all, right? So that's one case. So you need to optimize this because this is too naive. So as drawbacks, first drawback, as he said, read only shared data. Right? So if everyone is trying to read only shared data, so all you need to take care of is initially a thread is being initialized. At that time it will be written, and after that everyone is trying to read it. During the initialization phase, if we are sure that no multiple threads is trying to write there, then it should be fine. But the problem is it's really difficult to figure out when the initialization part is done. So what this algorithm tries to do is consider initialization to be complete when shared data is first accessed by a second thread. So the thing is, if there is a variable which is being initialized by a single thread and it is following a sequential order where it is trying to read the data and then write the data, and the same thread is doing that, then it should not be a problem. So that's what this first solution is saying. That's all. And then report an error only when the data becomes write shared, and if the second thread is trying to write it.
For initialization, you mean writing the writing the
Right. So you say int I equal
So
to
why do
0.
you separate initialization and writing?
because to consider this case of read-only shared data, if while initializing, if there is one thread which initialized a variable and is trying to read and write all the time, and no one else is accessing that,
It
that
may be
should be
clear
fine.
if you look at the state machine.
Right. So this is the state machine which they came through, and there is this virgin state, is like basically the initial state when a single thread is trying to read. First it initializes the variable, then it is reading and writing, and no other thread is accessing it. Then it should be fine. There will not be a potential database. But then, so initially when the initialization is being done, it is in a virgin state. When that thread itself tries to write something, it becomes exclusive. So now that data, which is being accessed by the same thread all the time, is in an exclusive state because no other thread is trying to access it. Right? So it will remain in executing exclusive state if the first thread itself is trying to read and write all the time. So its state will not change.
So can we think about an example in which this might happen?
Exclusive state?
Sure.
Okay, so basically suppose if there is a program and it allocated some memory and it is trying to read and write from that memory all the time and no other thread is trying to access that particular location. In that case, we are fine.
How could this happen? Well, I think one simple example, which is very common, is that you might create a bunch of memory which becomes shared eventually, but to begin with, maybe you only have one thread. And so you start off with that one thread, you
Right.
allocate some memory, you give it some initial values. If you've only got one thread, it doesn't make sense to even
Right.
worry about what lots are being held. So this is exclusive.
Right.
Now you can generalize that. Maybe there are other threads, but they're not interacting.
Yeah.
That's okay too.
I have a question, well, regarding this scheme and so on and so forth. So what if we have situation where we have some variable, it became shared when we spawn multiple threads,
Mhm.
but then threads will end up their life, like they did processing, and then we back to one thread. Should we go back to
So-
the virgin state?
So the thing is, after the barrier is over,
Uh-huh.
and at that time it would be in shared modified state, and then you came back and this thread got over. It's really difficult to tell when.
Is there anything that we might have talked about already which might inform us about that relationship? So this is a very good question, and this is the kind of thing that some of the successive papers that came after this started to look at as well. Because there's this general notion of maybe an object protocol, ways in which you can interact with an object that are valid. And this is looking at certain sets of these protocols in which you can interact with objects. But if you have these multiple phases, then you introduce other issues. So how can you generalize beyond just this notion?
Okay, just imagine. I thought of an example like there are multiple threads
Mhm.
and the thread got over, but the programmer didn't free the memory. And there is now only one thread which is trying to access and go and modify that location. So there will be memory leaks happening over there.
Don't even worry about memory leaks. Memory leaks don't have to come into play for this. So I think if we try to look at the relationship here that you're capturing, right, is this notion that you've got maybe one thread, it initializes things, then you've got two threads, and maybe they access things safely. And now you want to go back to one thread, and you want to be able to say that, well, since these two threads have come together again, there's no potential for conflict, right? This relationship where we're looking at this maybe partial order of events is interesting. Where do we see partial orders of events discussed earlier?
Yeah, during
What technique was that?
happens before.
Happens before.
Right.
So the happens before relationship isn't something that you necessarily want to just throw away. It's still an informative relationship there. If you just disregard it, then you'll get false positives.
And that's one of the potential weaknesses of the paper. Yeah.
It's one of the things that follow-up work might have looked at as well.
Right. There is this paper called data analysis, dynamic analysis by Fast Track, which takes a look at that problem and does it in a. There were a lot of papers actually. There are
Yes.
some 100 or something citation district, 1,000 I guess.
Thousand.
Thousand,
more
yeah.
than 1,000 citations.
More than 1,000 citations. So it's really difficult to follow up everything for one presentation. But yes. So.
The last 20 years of research.
Yeah. I mean, this is an older paper, and I think a lot of you
Yeah.
started to notice that there's some historical aspects here that are interesting.
Right.
Oh yeah, Netscape Navigator.
Yeah. Well, I mean, even when I presented the Delta debugging stuff, you did perhaps notice that I what were you here? You weren't here for that. Okay. I had the Netscape Navigator logo on the slides because a lot of these things are somewhat foundational. And you can see that there are differences in terms of the styles of the paper and in terms of the complexity as well. This paper, I think, is relatively simpler than some others. It's not necessarily a bad thing. It's more foundational.
Right.
So there wasn't that pressure to be complex in order to get published.
Right. This is like really like all the operating systems and all the Notion, they all use this concept now mostly.
Yeah. I mean, this is
Even-
pervasive.
Right.
Now, there's a lot of work on addressing some of the issues that you're talking about as well. But again, Thread Sanitizer is a tool that can do very analogous things that's built into Clang. It's now built into GCC as well. You can compile with it and just use it. It's pervasive stuff.
So yeah. So once you come to exclusive state, if there are threads which is just trying to read stuff, then it goes to a shared state. Until the time everyone is reading, it's fine. It is in the shared state.
So are people comfortable with the notion of initialization then, which is I think where we got sidetracked? Okay.
Yeah. So after it's in the shared state, all the threads are trying to read it. It goes to, and if a new thread is trying to write it, it goes to a shared modified state.
Why is that shared state okay?
Why is the shared state?
Yeah.
What?
So we talked about initialization.
Right.
After that is shared reading.
After that, it's exclusive.
Right. But so you've got that from the initialization. After that, we have the other problem of things like shared reading.
Right. Shared reading is again, if the first thread, which was exclusive earlier,
Mhm.
was trying to write at that time, it was fine.
Mhm.
But now when it is in shared, it cannot write.
Okay.
Because now if it is trying to write and the others are trying to read, there can be a potential database.
Why is shared reading okay?
Because now nobody is trying to write. So the data is same and its
Right.
consistency
Right.
is maintained across the threads. So
Right.
it is fine
Right.
to read. So from shared, if now if someone tries to write, then it goes to shared modified state. And again, from exclusive also it can go to shared modified if a new thread is trying to write it.
When do you change the lock sets?
So the lock sets don't change throughout the execution of the program. So throughout the program execution, the CV set.
Okay. I
remains
should
same.
rephrase that. That's an implementation aspect.
Right.
When do you change what the current lock set for a particular variable is? It's related to these states, right? Because
Right. Right.
clearly you don't care about changing the lock
Right.
sets when you're exclusive.
Right.
So what about when you're shared? What about
So-
when you're shared modified?
Right. So when you go to a shared state, so we'll go as we go forward. You'll
Okay.
see there is a notion of candidate lock sets where it tries to store a lock set along with the lock set index, and then it accesses so whenever there's a transition, it will go and update this data structure,
Okay.
and then
it's-
it will take a look at that algorithm.
Sure.
So what are the drawbacks? As we already discussed, that you still have a multiple reader and a single writer problem, which is not a data race, but it's in the programming aspect like everyone programs that, but this is not addressing to that. So we again modify the algorithm. So what we did is the first part is same as before. So lock set held is a set of locks held in any mode by the thread. And then there is a write lock set held, which is a new notion which they brought. And this talks about the set of locks held in write mode by thread P. So now you have two different sets of locks. And for each variable V, initialize CV to the set of locks as before. And then on each read, it's same as before. On each write, now CV does an intersection with the write locks. And if the set is null, then it issues a warning, basically. So now,
Why do we make that distinction?
So this extension talks about, now suppose if, okay, so these were the logs head and everyone is trying to, so there is a thread which is trying to read, then in that case the intersection becomes new one, and then if a new thread comes and tries to read it, write here, then it should have this lock. So we'll have a new lock, say mu3, which is a write lock, and this is trying to read, and there is a new thread which is trying to write. It should have all the write locks.
Right, so essentially the issue is somewhat that if you're holding a lock, but it's a read lock, it doesn't protect you.
Right.
You need to have a write lock in order
Yes.
to have that exclusivity.
Right. So, okay, so the concept of candidate locks, basically. So we did talk about this CD and all, but how is it implemented, where is it stored, and how do you take care of all this? So the implementation aspect, if we look at it, then basically this program captures only heap data and data segment. So they assume that if something goes to stack, then it is not probably shared, because every thread has its own stack of variables. If it is in the data segment, then they do check it, and if it's a heap, then they do check it. And the basic problem of this whole procedure is this algorithm is that it becomes huge, it becomes slow because of all this data structure which they take care of. So basically what it's doing is, when a program executes, it makes a log of each and every thread which is trying to read and write. So for each memory access, you have a separate place where you keep a log for that, which can be expensive. But since it is a testing program, it's fine at that time, when it was like 10x to 30x overhead of this thread, this execute.
Can anybody think of ways in which we might cut down on that overhead? Just speculatively?
So to reduce 10 to 30 slow down somehow.
Well, so let's not worry about what their actual slowdown is.
Mhm.
But so their underlying process is that you're looking at every read and every write that's executing, and you're maintaining this metadata, which we can see is also maintained in a shadow table.
Right.
We've talked about shadow memory before, so that should be a familiar concept, right? And they're maintaining this as maintaining this in such a way that the information stored in the shadow table is just an index into
Yeah,
the
I
successive
can
logs,
explain that.
right?
This person.
Okay.
Do the reads need to be monitored?
Do the reads need to be monitored?
If you
False.
Yes, depends, right? If someone is trying to write and you're trying to read the same data,
Okay.
and then the
but if you only monitor the writes, database has to occur with the write.
right, but you don't know then if other thread is trying to read it or not.
Yeah, I guess.
You at least need to know that somebody else is trying
Yeah.
to make a conflicting access. Yeah.
Yeah.
So you need something there, but maybe there's some way of making it a little bit more lightweight. There are some analyses that try to use biased approaches so that when you're just reading, the instrumentation is as lightweight as possible. And when you're doing something that's writing, you do some more heavyweight instrumentation. Since writes are less frequent, it's...
Right.
Is there anything else?
Right, so for example, there is a notion of thread local, thread private,
Sure.
and all these logs with GPUs and other accelerators, right?
Okay, let's think about that for a second. Thread local and thread private.
So basically what it does is, they have a shared memory, and within that they have a small cache, and within that, and that is specific to each thread. So now if I'm accessing data which is within my small memory, small cache, and I'm accessing only that data, and I have already been provided with a lock saying that this is exclusive to you, you don't need to take care of all this, because you know, which is ensured by your operating system, that there will not be a problem.
Okay, so sometimes you can know that you don't need to instrument some accesses. In this case, you're saying you've got some guarantees by the operating system. Maybe you've got some other ways you can figure that out as well. So let's think about other programming languages. This is pretty low level, right? We're talking about essentially native code. They do binary, some binary approaches here. What if we have a Java program? People know how concurrency works inside Java programs?
Keyword. You
Hmm?
can use synchronized keyword.
Okay, you can use a synchronized keyword. What types of data do you need to monitor in a Java program?
Only shared data.
Only shared data. Okay. How is that different than all?
Not all data is shared.
Well, can anybody think of stuff that isn't?
Private.
Yeah. Private variables.
Well, private variables can still be shared across threads. Right? You can have an object that there's a reference to it in two different threads, and that means that data is accessible in both of those threads.
Okay. Local data.
Local data. What do you mean by that?
Local to the thread.
Local to the thread. There are a few different ways. You have thread local stuff, just like with low-level programming. You have a notion of thread local data, explicitly declared thread local. You've also got things on the stack. Stack data is all unshared in Java.
Okay.
So these guys are not they are not looking at that stack data. So that program memory is only for heaps.
That's
So
that's
they are
fair.
already-
Other techniques do actually look at the stack data. But you have this notion of, can you figure out some way of identifying this data that
Right.
isn't shared? There are also analyses known as things like escape analyses, which are static analyses that are essentially best effort approaches to identify those variables that could be shared. And any variable that cannot escape its thread doesn't need to be considered. And you can identify that statically and just not instrument it.
Yeah, that would just be found through dependency graph, like dependency information.
Largely, yeah.
But that's an over approximation.
But you want to be conservative. So there may be some things that don't escape that you can't identify. You want to make sure that you identify things that,
Must not.
yeah. Or looking at it the other way, anything that may escape needs to be instrumented. Yeah.
So, yeah, the implementation aspect. Basically, what they observe, like the distinct sets of locks are generally very small. So that's why they came up with the concept of shadow word, shadow memory, as we already talked about. And so what it does is basically it only looks at the first 30 bits, because they use the other 2 bits for saving the state of the variable. Now, can anyone think of a problem with this? Because they are only trying to access the 32-bit data.
So like once we got 64,
Then they'll have
So-
some different implementation. Let's stick to 32-bit. And in a 32-bit machine, can they have a problem with this implementation? It's a 32-bit word, and they're trying to generalize it since it's a distinct set of logs. And they're only taking the first 30 bits, which is fine.
So how many logs it gives to us? Like 2 to the point of.
That is fine. So all the set of logs will be stored in a log set index table, which is also fine. But there is some problem over there. Think of instruction set architecture for Intel, for example. There are some instructions. Which is a problem.
There are some instructions that what?
So in Intel instruction set, if you look at those basic assembly language, move AX and stuff like that. So there are loads and stores, right?
Mhm.
Not all loads and stores can be 32 bytes. There are loads and stores for 8 bytes, 16 bytes, and stuff like that. Right?
So you pad them.
So
with
there will be a
zeros
log
and-
for only that 8 byte. But they are not taking a look. They are not taking care of that.
But it fits within 32 bits. So
Yes,
it's a word.
it is within 32 bits. Say there is one thread which is trying to access the first 8 bytes loads, and there is other thread which is trying to store the other thread, which is another 8 bytes,
Oh, it's,
and they lie under the same category.
yeah.
They won't have a different set of logs.
So what
you
is
are
this?
over approximating.
Right. So what does that result in?
So basically, you have 2 threads. They'll have the same index for their logs, and which can cause a problem.
Yeah. What's the result in terms of how this affects your analysis results?
False positive, false true.
False positive.
False positive.
Just in terms of the context of the analysis, yeah. False positive.
Right. Also, indirect addresses. Indirect pointers, which we already have a problem with. So, yeah, indirect pointers can also cause a problem. Right? Okay, so now this is a shadow word where you have state 2 bits for the state, since we have this four states over there as we saw, and the next 30 bit is for lock set index. What it does is it goes through a hash function and uniquely identifies the lock set index table, which is important, and then it stores all the locks in that index, and that's how candidate lock set is implemented.
So this idea of not creating redundant versions of the same lock set by using a hash lookup is often called hash consing. This is a very common technique to avoid redundant state that can be combinatorially explosive in some different use settings.
Hash cons.
Hash consing, yeah.
Okay.
Constructing.
So this is the implementation of candidate set logs. Problems, yes, false positives, as we already saw. So the thing is, if it is always false positive, it's fine, it's still fine. But now we are thinking of false positive all the time, but there are some cases where if you can come up with false negatives, then it's a huge issue because you're never sure what it is. Like you're never sure how much of the bugs we found.
But can we think about how you might have something that is some sort of a false negative?
Has doesn't execute, has that contain the shared.
Okay, you might just not see it. Yeah, because it's dynamic. Right. Suppose that you do execute a path that exhibits a concurrency bug. How might we miss it?
Would that be simple race condition?
Deadlock.
We'll come to that.
So what do you mean by simple race condition?
Would they have mentioned that they were only, if there were only like a simple block discipline?
Sure.
Maybe not.
This is true. So you could have multiple types of locks that are used. Ideally, that should result in false positives for them. Although in some cases it could result in false negatives too. You could also have a scenario where what they're doing is essentially saying you want to have a consistent locking mechanism, right? And so that's how you avoid data races. And the issue with data races is an inconsistent view of state across threads. Ultimately, that's what it leads to. An inconsistent view of program state across threads. So how can we still get an inconsistent view of program state? Well, if you make your locking very fine-grained, so let's say you've got a read of a variable in this thread and a write then following it. Well, you could put a lock around both the read and the write, and that means that the behavior is atomic. So you do the read and you do the write, and the write corresponds to that read. But if you make your locking very fine-grained and put a lock around the read and then put another lock and unlock around the write, well, you don't technically have this same notion of data race, but you've got the same inconsistency.
And in their case, they do detect the read after write, but write after read gives you a false negative.
And they can't detect this at all, though,
Right.
because you still have locking discipline.
Right.
You don't have atomicity. It's not executed all at once.
If you don't use locks, you also just won't
Very true.
pick up anything.
Yeah, there a lot of the newer techniques try to sometimes even ignore the locking mechanisms that are used and just look at the access patterns. And there are certain patterns of behavior that you can detect across threads that are indicative of this more general notion of an atomicity violation.
So there is a case of benign races, basically true data races, that do not affect the correctness of a program, because the programmer wants this to be fast, and they don't want to have a locking overhead.
This
But
is
this will give you
also
error all the time.
this is also something that people used to be all about recognizing benign data races. This was a very important thing because this was a source of false positives. I would say if you have a data race, it's horrible. It is a sign of a bug because a benign data race may work. A data race may be benign today and not benign tomorrow
Right.
because data races are undefined in the semantics of most programming languages, which means how the compiler decides to lower that code can be different.
As they pointed out in their operating, there's one operating system where they tried this. The thing is, they gave an example where the operating system may not follow the semantics for this one,
Yeah.
and that can be a huge issue. So you never know whether today it is true, today is fine. Tomorrow when something new comes, it might
Yeah.
not be. fine.
There's some great
You should always
papers
try
that
to
go
avoid
into detail about how benign data races are a fallacy. It's just an incorrect notion.
Are they, please tell me they're still not used in programming? Like, they seem to be an accepted method of programming in paper in '97.
There are a lot of things that are accepted today that shouldn't be.
Okay.
I'll leave it at that.
Right. The thing is, programmers want their code to be fast, and so they put all those things. But it
No,
might
I can
lead to
give
problems.
example. For example, you have several threads increasing the counter, and you don't care whether, and you want to start when the counter reaches 10,000, and you don't care whether it's plus minus 1,000 or so on. So forth.
If you don't care about the result,
Right.
then that's okay. Because
And
you've
it's-
explicitly said you don't care what the actual result is. It could be the case that because you've done that, it's not plus or minus 1,000, it's plus or minus the entire result.
Okay.
And it can also happen that you are writing a small module in a company where you know for your module it's not important, and there is this other guy who thought, okay, this is the precise thing, I'll use this variable to make my own thing because it's object oriented, right? So in that case, ultimately when the whole module comes and say if some important parameter is based on what you made, it's a useless.
Then atomic plant station explodes because they use your module.
One of the big problems is that compilers today assume that there are no data races. And so the optimizations they perform on your code are only correct if there are no data races. And because compilers are increasingly powerful, this has greater and greater effects every year. So this is why you get surprising errors, why this can introduce surprising errors if you have supposedly benign data races.
That's why compiling older and older code gets worse and worse and worse.
Yes, right. Because it was technically incorrect before, but the compilers didn't express that incorrectness.
After this course, we're gonna go to Intel and gonna make compilers.
So other causes, private locks, because they implemented a standard pthreads. If you are using your own set of locks, then it's a problem because it won't detect it. And the first one, memory reuse, which talks about, for example, there are OS data structures like FreeList, and there are some private allocators. This can cause a fault. How?
They just don't consider them at all.
Right.
So they, okay, pthreads, but there is so many others right now, right? There
Sure.
is this OpenMP also provides you.
Right.
This is
So
2002
they
paper.
won't.
So dealing with this is one of the other hurdles. Most infrastructures today manage this by updating their library, their recognition of commonly used thread libraries, and providing annotations that are easier and easier to use in practice for recognizing domain-specific threading mechanisms or synchronization mechanisms.
So basically what it tried to do was add a couple of flags to basically reduce the number of false alarms, and that acted against them. So there is a quite specific example, as we already talked, where it gives false negatives, which is really horrible. So the strengths of the paper, basically it is a very detailed and well-written paper in terms of how they express their idea, which is a good thing, unlike the previous one we saw. And so yeah, I like the paper. And yeah, they tried to implement it through a dynamic approach, which is not pretty common. Weaknesses from false alarms, slow runtime, not enough numbers of statistics in terms of graphs and all the running it on standard benchmarks and stuff. I'm not sure if they were present at that time. So
The approach back then was much more anecdotal. And I think you get that impression reading this. They're
Right.
telling a story. There's a narrative presented in the paper more than we have hard evidence.
Right.
And this is still true in some areas of computer science today, but it's less common in most areas, which is a good thing. It's harder for us to publish, but it's a good thing.
Some thoughts, as we already talked about it. There's Apple data in multiple programs and website local log protected, we've shared, which they never considered. And yeah, all senators talked about it.
Yeah. And you can see this isn't a panacea. They make a lot of claims about this being better than Lockset, but there are ways in which the two approaches are both better and worse than each other
Better than
individually.
happened before.
Sorry, yes, happened before. Exactly. Yeah.
Yeah, there were a couple of papers we saw which implemented happens before and they provide precise
Mhm.
database handling, which is really good.
There are also other papers that start to look at the object protocols a little bit more, and things like object-oriented protocols, which are maybe a little bit different than just the state machine we saw here.
I
And
think
so-
someone's presenting that, right?
Hmm?
You mentioned in the previous class where there is just one paper which talks about only C and C++, and they have a detection for.
I think that was for looking at test case reduction.
Yeah.
Right,
okay.
so this is a case where we're looking
Right.
at data race
Data race.
detection,
Right.
and they actually have, there's a different set of protocols that are common in object-oriented systems. So you can be very domain-specific and look at the exact types of protocols that are common, or maybe try to infer the protocols.
That's,
Sure, we might be out of time. But I think this was probably a clearer paper, right? I'm not sure that it was necessarily well written by modern standards in
Right.
terms of the detail, but it was a much clearer paper. It was easy paper to read. Yeah, by far.
I like the idea of using undergrad coursework as a test.
It's risky.
We should use our own programs to test the.
Dog fooding is good, it's maybe not the best evidence.
Yeah, as soon as I saw that, I just was
Yeah.
like, I didn't like it.
The question is how would I